Okay, everybody, let's get to it. So last time we were talking about energy transfer by heat. We knew there's two ways that energy can leave our control volume if it's a closed control volume. One was heat, one was work, and who would have guessed we are now going to talk about work. So let's jump right in. So work is simply any energy transfer where a force is acting through a distance. Now, if you've taken physics, you should know that work equals force times distance. Force, distance, it's all there. Now, that's a very simple form of work, at least that equation. Because like I have a rising piston, a rotating shaft, electric wire crossing the system, all of those can be work as well. At least when we're talking about thermodynamics. We don't really care how the energy is getting out, but if it's not heat, if it's not based on a temperature difference, we call it work. Okay, now here is the sign convention. And I do hate how they show it here, but we're going to talk about which one's positive, which one's negative. So, if I do work on a system, the system gains energy, okay? If I put heat in a system, the system gains energy. If the system does work, then it loses energy. I probably should put this right here. There we go. And if it sends heat out, well, obviously it's going to lose energy. Now, there is an absolutely, well, in my opinion, amazing way of thinking about this when it comes to work. Okay, now think about it this way. You wake up in the morning and you got energy, okay? You know, the alarm clock goes off, it's not too bad, and then you go to work. After work, how's your energy levels? Well, your energy levels probably plummeted. Now it's down in the low part. So what do? Maybe you go and get a massage. After that massage, suddenly you're feeling great. So, let's go back to our analogy. You had energy, you went to work, you did work, and because you did work, you lost energy. Your energy went down. But then when you got to get that massage, somebody worked on you, and because they worked on you, you gained energy. So, use that to help yourself. If your system is doing work, producing power, any of those things, then it is going to be losing energy. If something is working on it, compressing it, whatever it is, then it's gaining energy. So think about that. Make it easier on you. Okay. Now we see, we got this right here. Okay. Let's look at a few little relationships here. The biggest thing I want you to see is capital W, dot W, and a lowercase w. Okay? What are they? Well, capital W is simply work. Lowercase w is work divided by mass. And capital W with a dot is saying work over time. Okay, work over time. So I had 30 kilojoules of work. That happened over 5 seconds. 30 divided by 5 is equal to 6, which is how I got the word W dot. I had 30 kilojoules of work over 2 kilograms. And so when I divide those together, 30 divided by 2, I get 15, which is what I have right there. So that is a relationship. So be very careful with your dots. They do have a particular meaning. Okay, they do have a particular meaning. Okay, keep it on. Now, this right here is what's called a process diagram. This is pressure. This is particularly volume right now. Usually we do specific volume, but we're just doing volume right this second. Now, this is something that you're going to see all semester, and if you go into applied thermo, you'll see it again there. It doesn't go away. So what does it show us? Well, it shows us quite a bit. For example, I have two processes here. One is process A, the other one is process B. And they both go to two different states. This is state 1, this is state 2, so they end up at the same place. They have the same pressure, and they have the same volume. However, they took two different paths. Now, what we're going to be learning about a lot this semester is that the path you take matters, because you can take a very efficient path or a very inefficient path. You all know that. You know the shortcut to get your house, probably the slow or the fastest place to get there. But if you take the wrong way, well, it's going to take a lot longer to get to the same exact point. Okay, let's see here. Now, heat and work are all about when we cross a boundary, okay? And they are associated with a process. Process is simply this path from one spot to the other. The thing they are not is something we see at a particular point. There is no such thing as the work of a state. That means that I stop moving, there's no work. There's no heat there. Heat, work is all about movement, it's all about transfer. Is it going from system A to system B? Great, there's heat, there's work if it's going from one place to another. But if I'm just talking about a particular system and nothing is changing, then I don't care about that. The work is not like magically a property of the system like temperature is. That's a property. I can measure temperature. I can measure pressure. I can measure density. I can measure volume. I can't measure work for a particular point. I can only measure work by seeing how things have changed. I see work based on how the energy in my system changes from one to the other. Another thing this shows us is that if we have a particular path, there can be more efficient paths. If I look at process A right here, it only takes 8 kilojoules. Process B takes 12 kilojoules. It's actually quite a bit more. And interestingly enough, this area right here would be 4 kilojoules. Why? Because the work you do for a particular process is the area under this line. So that area right there, if I were to convert the units properly, would be 12 kilojoules. And if I were to do it for this one, it would be 8 kilojoules. And so that leads me to guess that 12 minus 8 is probably 4. Very helpful thing, and also shows us how we can do this numerically. So if we actually had a perfect graph like this, we could actually figure out the exact amount of work without having to do any equations, just by adding up a bunch of rectangles. Okay, I think this is the last one for us here. I'll pull this stuff up here. Boop. Now, electrical work. It's something you're also going to see because we will have heaters, we'll have generators, all kinds of things where we are creating work through electricity, not necessarily through movement of physical matter. Well, I guess electrons are physical matter, but movement of big things, but through movement of electrons. So, electrical power for us, voltage times current. You're like, wait a second. Yes, this is another V. This is voltage. Okay, this is voltage. And let's see, right here, we can also do this over time if we want to, and we can figure out how much current we have. This might be something a little bit more common for us because usually we don't have a voltage or a current in this class that is changing over time. Now, in all honesty, you're not going to use these equations all that much for this class. Not saying you won't ever use them, but typically we don't ask what the voltage is for the pound of work you're doing. We just simply say, there is electrical work going into the system of a certain amount of power. I'll probably say that there's 50 kilowatts of electrical work going into the system. And that's what we typically give. So I don't usually give you resistance and current. I usually just give you a number. And so it'll make things a lot easier as we go forward. Okay, I believe that's everything for this one. Yep. So thank you all for listening. I'll see you all next time. Have an absolutely wonderful day. Bye-bye.